In order to understand the Bayes rule a little bit better, I'm going to show you this visual analysis of all the probabilities that you see in here in the calculation. In particular, I want to show you how the prior probability and the quality of the test are affecting the posterior probability, this 9%. So I created here a little chart or table that shows you the following. Suppose we have 10,000 random people that we will test. Now, among those 10,000 people, we would expect 100 people to actually have the disease, not test positive, but have the disease, and 9,900 not to have the disease. Why is that? Well, because upfront, remember, we assumed 1% chance, a prior probability for having the disease. 1% of 10,000 is 100, and this is the 99%. Now, among those 100 who have the disease, we know from sensitivity that 98% of them should test positive. But unfortunately, there is 2%, right? Negative, false negatives here, right? Even though they have the disease, we expect 2% of them, which is 2 people in this case, to have a negative result, right? And now the same logic we can apply to those who don't have the disease. Remember, those who don't have the disease, we said the specificity of the test is that 90% of those who don't have the disease test negative, which is the correct result. But there are also false positives. The remaining 10%, which is 990, right? 10% of those 9,900 are people who test positive, although they actually don't have the disease. So now consider right? I hope it's clear how these calculations are done in the columns. Now consider the row. In the first row here on those two, you have all the people who tested positive. The 98 are those who actually do have the disease, and 990 is those who tested positive, but actually they don't have the disease, right? These are the joint probabilities from the Bayes formula. So now you can see that the total number of people who tested positive is 10,088. And notice that can give you the reason why, this is the reason why we calculated probability of being tested positive as 10.88%, because this 1,088 out of the original 10,000, it is 10.88%, right? But what's more important in this case is that out of those who tested positive, 1088, only 98 actually we expect them to have the disease, right? So the probability that somebody is positive, has the disease, is 98, given that they tested positive out of 1,088, and that's only 9.01%. Why is this asymmetry here? Why is this probability so low? Because there is an asymmetry here, right? There is such a huge bias in the original sample. We only have 1% of people who test positive, and even if who are positive, and even if 98% of them test positive correctly, right? The small, relatively small 10% of those who don't have the disease who incorrectly test positive is so much larger than this 98, right? Those who correctly test positive. And because of this, right, because of this disproportion, the predictive power of this test is so low, right? It's only 9.01% that are correctly that will actually have the disease when they tested positive, right? Of course, if the initial breakdown, also the prior probability was much higher, this breakdown would be different, and this disproportion here would be smaller. The other thing that would, of course, affect it is if here the sensitivity was higher, not just 98%, but maybe 100, and in here the specificity, if it was higher, right? So the false positives, the 1 minus specificity, which is 10%, the false positives, if this was smaller because of a better correct identification of negative cases, this would also help drive this probability much higher. So this kind of visual representation of the test might help you understand a little bit better why this probability, 9% probability, conditional probability to have the disease, given that you tested positive, somebody tested positive, is still so low.